Hello, everybody, and welcome to the third session of today's ATypI Tech Talk. And I'm your moderator, Eric, speaking here. And this session, we are very pleased to welcome three Chinese speakers and giving us the session which title is Computing the Shape, Parametric Fonts, and Hanzi AI. So here in the session room where we have Yehang and Chen Zewei. And what a pity that Zhang Rui cannot join us here. So maybe we can begin the playing the video, and everybody is welcome to have the chat. If you have the question, you can chat or ask the question down in the UI. So all the question and our speakers can see it and answer it later.
Hi, my name is Yehang. I'm from Next Lab, Zhejiang University. Our team focuses on applying tech to the design of Chinese characters to make it faster, more efficient, and more interactive. Our topic today is called Computing the Shapes, Parametric Fonts, and a Hanzi AI. This story is about why, what, and how to automate Hanzi design. I will be here sharing our work on the Chinese characters, but I also hope that this story will inspire the type design community a little bit to see the potential of parametric fonts and artificial intelligence as a tool to liberate everyone's creativity. So, first things first, why do we need to automate CJK type design? The very simple reason is that these writing systems involve Chinese characters, or Hanzi, which takes up most of the code points in the Unicode. We may have already heard about this story several times, but I will still go over this part, since this is a new version of the story. Our topic, Chinese characters, is also known as CJK ideographs, or Hanzi in Chinese, Hanji in Japanese, Hanja in Korean, are different transcriptions of an identical word when written in Chinese characters. In this presentation, we will use the term Chinese characters, or sometimes Hanzi for short. So how does the Chinese characters work? Some Chinese characters are pictograms, like the character for a net still looks like a net. The character for air comes from a doodle for the air. The character for knife used to look like a knife. And the character for the goat was in the shape of a goat's head, etc. Other than the pictograms, some characters are ideograms that express more abstract meanings, like the character for one, for to separate, for up, for concave, and so on. Importantly, there are combinations of those building blocks to make compounds. Components in the compound can be either thematic or phonetic. For example, the character for oxygen is made up of the air, which is the semantic component, and the goat, which indicates how it should be pronounced. There are also multiple ways to put the components together. The components can be spread left and right, up and down, or even in and out. We can also make compounds out of compounds to make super complex characters. One famous example is this biang, a folklore character for a Xi'an noodle dish, biang biang mian. But of course, most of the Chinese characters won't be this complicated. The story of Hanzi doesn't sound complex to the very first impression, actually. Like many non-alphabetic writing systems in the world, we make combinations out of some basic components. However, what drives people crazy is that it isn't always this logical, as the system has undergone a non-stop evolution for quite thousands of years. Shapes of the components may alter by their positions, like when putting a component to the left side, you must tilt the last horizontal stroke. This eases the writing a little bit, as it decreases the total distance of a pen, but you can't make this tilt in modern Chinese characters, which means that you cannot simply put two original forms together, to make up this compound, you have to alter the left component. There are also more complex cases in which we do not see any apparent reason to alter the component. Like the net we mentioned before can look very different in characters. The net components may look the same in their historical forms, but they evolved to look totally different. Strokes may also stick together, and quite a few shorthands have become the convention. You just can't write correctly without these shorthands. An example given here is the character for the concept restrain. It's made up of a semantic component, which is a pictogram of a sitting person, and a phonetic component marking the pronunciation. Historically, you can distinguish these two components in the compound, but ever since an early development stage of Chinese characters, the two left fallen strokes merged together, and thus the modern form emerged. All these exceptions mentioned in these slides introduce isolated wicked problems into the system and make the story of Hanzi so complicated. But why is it hard to design anyway? A short answer is because of the complexity of individual glyphs and the tremendous character set. When you put the Earths that are positioned to the left all of the others, you will find they never completely overlap. The actual size, position, and shape of a component vary by characters. And you've got thousands of such headaches to go. The real number of Chinese characters is perhaps the infinite. It's basically an open set. Even though CJK type design is already physically hard to do, you have to make it perfect. Generally speaking, designing a good CJK font is all about making the glyphs look good and look good together. On the contrary, spacing isn't usually a big issue. So how do we design CJK typefaces? Here is a rough conceptual model based on interviews with Chinese type designers. To resolve the complexity, you need teamwork, loads of teamwork. Before you want to make your font a product, you can get everything done all by yourself. This is the phase of prototyping. You have an idea, you try it out, sketching whatever characters you like, and as your work accumulates, you will go back to fix some of the designs, making real design decisions, and keep this experimenting and defining cycle before you think it's to your limit. Once you set up your mind to fill out those thousands of vacancies in the character set, you will have to collaborate. Even if so, the project will cost months. In order to collaborate, your design has to be well defined so that your teammates can also produce the glyphs in the same style. And here comes a new cycle of production and revision. Previously defined strokes and components will be reused and edited to make up new glyphs, and then being reviewed and revised until it gets perfect. This heavy workload raises problems, not only on the type designer side, but also on the type user side. We have just mentioned that you usually have to work with a team to design Chinese typefaces, and the size of a team that you have to work with depends on the project. 3 when the project is small, and tens of designers when the project is super big. In China, it's rare to see type foundries run by only one person. Very few individual designers would ever make their own typeface, because it's basically infeasible and not competitive compared to big companies. Even with a lot of people, it often takes months to years to finish a typeface. And there must be a few of your teammates suffer from the endless production stage without much creativity. To make your teammates not suffer so much, the principal designers have to be very careful about design decisions. It will be a disaster to go back. The tremendous charset problem makes CJK typefaces stress testing to font designing tools, and the engineering work is also a mess. These problems on the designer side also brings problems on the user side. They don't have enough choices, and the price is expensive. Because of the design and the engineering is difficult, most Chinese typefaces are not rich in open type features. There is also a lack of superfamilies on the market. I can't speak for the cases in Japan or in Korea, but I think you've got my idea. Type design projects that involve Chinese characters are naturally complicated. Again, designing CJK typefaces is hard. To sum up, it's a trilemma that you can't satisfy all the three aspects at the same time. We want the typeface to be in good quality and also covers a large character set, but the cost of human effort will also become high. This part of human effort is, in some sense, the non-creative human effort that we want to avoid in the creative type industry. As long as we create the shapes with human effort only, the trilemma will be unbreakable. The existence of such a trilemma is the ultimate reason why we need tech to automate CJK type design. But to use tech doesn't necessarily mean to compromise, as we generally believe that the automated design process will also provide more style consistency, since humans have individual differences and will thus introduce inconsistency into the design. But algorithms won't have such a problem. However, before the tag is advanced enough that we can fully trust it as competent as a well-trained designer, the trilemma could still not be solved. Because we shall still at least review and modify all the generated glyphs, so there is still a long way to go before we can finally automate the whole design process. The rise of digital typography finally gives us a chance to automate type design. Many of us had believed that there will one day come a fully parametric font system that will resolve all the headaches we mentioned previously. But will that day come? When we talk about parametric fonts, the very first impression may be Donald Knuth's rocket science meta font. He introduced the concept of meta design, that is, the design of the design. You have to be both a calligrapher and a mathematician to master the technique of designing a meta font. But as the concept of design space is becoming more and more complex in multiple master, it's also getting a little bit meta-designish to plan for typeface family. So what's the difference? I personally prefer using the word parametric font as an umbrella term for a whole range of technical methods and designing practices that control the glyphs with parameters. Here's a marionette analogy that I think best explains the idea. The puppeteer is either the designer or the end user. The strings are the parameters, and the puppet is the glyph or the font accordingly. Generally speaking, these parameters in parametric fonts are interpretable. In this sense, the definition of parametric font has become so broad that we need some classification to make things clear. Lao Manjing, in his PhD thesis at the University of Hong Kong, classified the methods into two categories: the procedural, in which the glyphs are modeled explicitly in a very meta-designish manner, and the learning-based, which generates new shapes from given samples. The world has changed a lot since Lao's PhD thesis came out. There are methods that are both procedural and learning-based now. So why don't we make it a spectrum? The procedural are to the left. To master them, you have to be super familiar with the mathematical tools that explicitly models the shapes of the glyphs. The learning-based methods are to the right. It's more about technical processing of the designer's drawings. Systems like Knuth's metafont are in the most procedural manner. Letters in the fonts are modeled as programs exposing several parameters for the user to modify the shapes. Back in the old days, there were also constraint-based parametric methods that models the meta design differently. The glyphs are not generated from codes. Rather, the codes define how the shapes could be modified. On the transition part of the axis, there are modern tools and methods that have both procedural and learning-based features. Some of the methods are now actively used in the industry. In some ways, they still feature what we know as meta design. deconstructing the glyphs into strokes or components, but they do not require much of the user's coding ability. To the right side are statistical learning-based methods. Such methods generate novel styles from given samples. These methods are often proposed by the academia in recent years and do not require much design expertise to construct the dataset. Most methods we listed here are designed for the Latin script. When applying those methods to Hanzi, especially the procedural ones, the complexity of the meta design becomes a reason why we couldn't choose such methods for this scenario. Therefore, in order to propose a method that is truly useful for the CJK type design, we decided to make it more learning-based. So here is our learning-based method using only one sample. The method includes a new font representation and a few Hanzi-specific operations. The fundamental idea behind this representation is not new though. We model the contours as skeleton points and offsets about the corresponding skeleton points. This representation benefits us for making it possible to separately operate the structural features and the stroke features. Based on this representation, we also defined a few operations to modify the glyphs. And here are some of them. These operations would modify the fundamental metrics of the Hanzi. The distortion-free scaling operation will resize the glyphs without changing stroke widths. We can also transform the gravities of the glyphs, as well as zhonggong, which in Japan, a similar concept called stokolo is used, which describes the structure's inward tightening. This concept is usually compared with X height in Latin type design. It would be a long story to make it clear, so I won't go through that story. Besides all those operations we listed here, we can also do things like changing the stroke width a little bit, changing the contrast, and so on. What's good about this approach is that it requires zero human efforts and is 100% automatic. So we don't need a meta design to do a lot of things. Here is the application. GlowSense, an interactive tool to generate new style instances from the given sans serif typefaces. This project is now open sourced. You can open this demo on your web browsers. We learned a lot from the Prototypo project, but as you may have already known, the Prototypo project relies on a few pre-built meta designs for the customization. With our parametric approach, we do not need to meta design every Chinese character. In this web demo, you can change many sans serif designing features using sliders, switches, menus to customize the styles you like. Except from the macro scale features we mentioned, we can also modify the very subtle design features like the stroke shapes, curves, and cuts. We also provided options for the supplementary leading and number typefaces. The user can also export the parameters to build the font later. With this interactive tool, we built an open source CJK typeface family, also naming GlowSense based on source HanSense, extending the original 7-weight design to 44 instances, consisting 5 widths and 9 weights, supporting simplified and traditional Chinese and also Japanese. GlowSense not only extended the source HanSense family, but it also changed the design to look totally different, to be more concise and modern, also with a hint of geometric flavor. Notice that we did not generate any new glyphs for GlowSense. What we did is to modify the existing glyphs. But why not? Why don't we use this technique to generate characters from a handful of basic components? Considering we have such a flexible and powerful parametric font method, especially we can transform sizes of the components without much effort, you may want to ask why it is still a problem to automate CJK type design. Can't we just resize the components, adjust their gravities and zhonggong a little bit, and get everything done as we wish? Yeah, we have tried that. The idea actually has a long history, ever since the early days of Chinese Gutenberg types. There used to be divisible types made by Western missionaries. Although they were faster and cheaper, we refused to use them for the simple reason that they look ugly. The emergence of parametric formats made it possible to make the divisible types combine in any proportion you wish, other than only several ways to divide and combine. But still, they look ugly. Such methods dating back to 20 or 30 years ago work in a procedural manner. Usually the strokes are modeled with programs, and the system combines the strokes automatically or manually. We did apply our method to compose new characters, but as you can see in this figure on the right side, apparently, the generated glyphs look far less satisfying compared to the ground truth. I here cite a conclusion in Wang and Xu's paper for designing Chinese typefaces using components in 1995. They said that Chinese font development is not surely a technical issue, but both a cultural and scientific matter. Well said. Combinations of the basic components doesn't work in a simple way. We sometimes overlook the fact that different technical methods have different functionalities. For the Hanzi design scenario, because the design process becomes complex, we must be clear about in which aspect does a technical method works best. There are actually two orthographic dimensions of the technical problems. One is the dimension of charset, the other is the dimension of style variation. GlowSense was most successful on the style variation dimension, but we found it hard to predict on the dimension of charset. It's also what the parametric methods aren't good at. We barely see these methods work well on the charset dimension. One reason might be the sizes, positions, and shapes of the components are hard to be modeled explicitly. Unlike using anchors to position combining marks in designing a Latin font, the rules behind making a Chinese character is much more complex to be written in pure mathematics. So here comes the Hanzi AI. We pour handcrafted shapes in and get novel shapes out. It works implicitly. It works on statistics. And it works in a way that we can't fully understand from the perspective of design. The story of Hanzi AIs started since 2017, when Rui Zhang open-sourced a deep learning model for Chinese typeface style transfer, naming 字兔字. The 字兔字model is an adaptation of pix-to-pix, which is an image-to-image translation model. The model is a conditional GAN and is trained on paired images. So basically, when you have two groups of related images in different categories, like photos of the same place taken in both mornings and nights, or the same picture in both black and white and color versions, you can feed them to the model as the training set. And the generator part of the model will learn how to translate image from one category to another. As shown in the figure, in category A are edges of the shoes, in category B are photos of the shoes. And you train the model on these paired data. So when the model later sees a new doodle of a shoe, it can transfer the image from a doodle to look like a photorealistic shoe. 字兔字 works similarly, but it works on Hanzi, and it works on multiple target categories. We call the A category as the source, and the multiple B categories as the target. The model will learn how to translate Hanzi in style A to Hanzi in the target styles. So this model can work on the charset dimension. Usually the typeface we use as the source covers a large character set, and what we want to make as a target is usually a typeface that does not cover as many characters as the source, so that we can transfer the glyphs in style A to novel characters in style B. In this way, we can get the glyphs we didn't design before. Such characters in style A are also called the content references. Hanzi AI researchers use the term content to describe the abstract representation of a character's topology. Then, what's new about Hanzi AIs? Why don't we think it's parametric? Why is this genre so different? Hanzi AIs, typically the deep learning-based methods, are unique because the design features in such methods are modeled implicitly. But in the traditional parametric methods, the design features are always modeled explicitly, even for the learning-based models. In other words, for the parametric methods, we always know what's happening, or what we want to make it happen. But for the deep learning-based methods, the model is designed on a higher level. Without many type design considerations, we don't know how the model gained the ability to design types from the training data. Form representations that the methods use are also different. The parametric methods are usually compatible with vector graphics, but current deep learning-based approach work mostly on bitmaps. Parametric methods are driven by rules, constraints, or data samples, but the Hanzi AIs only work on metadata. This also means that parametric methods generally requires a higher expertise in type design than the deep learning-based methods. The Hanzi AIs have evolved much since 自图自. Both recent models decouple the style features and the content features. Some models can generate glyphs in new style without being previously trained. Others add information to the network to improve the content learning, like making the model know what strokes or components are in the character. To solve the design efficiency problems on both style dimension and the character dimension, my co-presenter, Rui Zhang, proposed this MSEMV model. It features multiple style encoders to perform better in style learning. This model not only transfers styles but also fuses them. One of the interesting applications we tried with MSEMV is to fuse the three basic styles of CIK typefaces to see what we could get. These three styles are the serif style, also known as Songti, at the top, the sans style, also known as Gothic, at the bottom right, and the regular script style, known as Kai, at the bottom left. We can get any fusion in this triangle, make style combinations in any proportions smoothly, without previously drawing compatible multiple masters. But even with this MSEMV, we cannot generate the characters that we do not have a content reference. It is often the case that the character has not yet been encoded. Such a task is also known as the Gaiji problem, which has been haunted for decades. We look back to the good old parametric approach to see if a hybrid pipeline would help. And we made it. We first mechanically combine the components with our parametric method and then post-render it with a pre-trained image-to-image translation model. Such a model was trained on other parametric combinations and the corresponding compounds. This combined to compound network can turn the parametric combinations to good-looking results. With this technique, we made two animations. In the last animation, most of the occurring characters are unencoded. It's really exciting to see an AI generate Hanzi that did not ever exist, but still a pity to see them only in bitmaps. Yet, although current Hanzi AIs are already powerful, we can only get bitmaps. Since this tech genre is a branch of computer vision, it is still challenging to get quality vector graphics, which will help us more to improve the design efficiency. We've got a list of things to try out in the near future. to improve quality of generations and to bridge the rasters with vectors. How about a hybrid approach of parametric and deep learning? We've just tried parametric first, deep learning last. If we can figure out a way to make parametric to be the last, it will be promising to get quality vector graphics. The progress of deep learning on image synthesis is also surprising us, which may improve the quality of the AI-generated bitmaps like vision transformers and diffusion models, which made the DAO-in2 happen. There are also a few attempts for deep learning on vector graphics, including DeepSVG, as well as some methods that try to provide more fundamental mathematical tools for the task, like the idea of differentiable rasterization. Deep learning is powerful. We may also try it on other scripts to aid the design. From a user perspective, image-to-image translation is a task that is easy to understand, and the models that do this task, including pix-to-pix and 字-to-字, are, to some degree, controllable. When you have the right data to feed the model, it generally does what we want it to do, like turning the labels to facade photos, turning the edges to shoes, or turning the Hanzi from one style to another. What we can do with it is just a matter of imagination. Why don't we try Roman to italic, or serif to sans, or thin to heavy? There are just endless possibilities. We also saw the potential of parametric fonts and AI to make art more accessible to everyone. Seal carving is a form of fine art in East Asia. This art form hasn't always been appreciated by a wide audience because it is hard to learn. Traditional Chinese seal carving involves engraving archaic Chinese characters on seal stone. You have to look up in the dictionary, finding the correct characters for the seal, then make your own design, and finally engrave your design on the stone to make it a seal. In some ways, seal carving is like designing logo types, or we can take it as a fine art cousin of the punch cutting. We apply the Hanzi AI on generating the archaic Chinese characters and use the parametric method to allow the users to customize their personalized seal designs. Parametric methods does not require much computational resources, so it can run easily on a mobile web app. In 2020, we had an event to provide ZJU graduating students with personalized seal carving service. All the graduating students can get a chance to customize their class gifts on the app we developed. They can design the seals on their own, and we will later manufacture to engrave the design onto the seal stone. It's easy, interactive, and a lot of fun. Everyone could enjoy creating their own piece of artwork. Well, our talk is almost done. In the past 3 years working on automating Hanzi design, I have really learned a lot, and here I would like to share some of my views to conclude this talk. An important lesson I learned in the past few years is that we must give up parameterizing to construct a new Chinese character. I used to be a big fan of parametric fonts, and I used to believe that we can finally fully automate CJK type design with parametric methods. But after so many years of trial and error, I changed my idea. From the early divisible type practices to the modern days parametrically combining approaches, all those attempts failed. I don't think I'm smarter than those people. To conclude, there is no universal and explicit way to automatically generate Chinese characters. In other words, we cannot find a parametric method that works on most of the styles and structures, and at the same time, we can know how it works in details. So leave the parametric technique to the users to give them rich interactions, at least for Chinese characters. The parametric approach works better in the interactive scenarios, but they aren't really capable for very large style variations and generating glyphs on the charset dimension. Designing types is a matter of human. It's good to know that we can never know how the Hanzi compounds actually combine in pure mathematical notations. Even though I do both programming and Chinese type design, I haven't figured out how to write down the way I think when I'm designing types. I don't want my aesthetics to be written down in functions and equations either. But we won't stop our pace to automate CJK type design. There are two stories about the past that are always inspiring me to move on. These two stories are also related to today's topic. One is the emergence of Chinese serif face. The Songqi was an efficiency trade-off in woodblock printing. At first, people didn't like them, but after hundreds of years of evolution, it has become part of our culture. Another story is about the steel carving art. It used to be an applied art with very few calligraphers and craftsmen ever knew the technique. But curiously, it became popular among the literati in the 14th century, only because stones that are softer and easier to carve were discovered at that time. The stories keep reminding me that tag for design is to compromise, but also to liberate. Even though it had its bad parts, those bad parts may also evolve to become the good parts and integrated into our culture. It's better to be braver. In Mary Osman's Age of Entanglement, she proposed this Craig's cycle of creativity, which compares the four modalities of human creativity to a biochemical process bearing the same name. In this analogy, you get currency of creative energy when you transfer from one quotient to another. This analogy gives us insight on understanding how to view the impact of our work to the future. We are equipped with science and engineering knowledge to help with the problems in art and design. We hope that with our efforts, we can make the design faster, more creative, and the art have a wider audience. Some people are worried that this will ruin the creativity in art and design, but I'm personally most optimistic about this issue. Even though we make compromises, who knows if it will become a part of the culture and humanity? We shouldn't fear the AI. And after all, the Hanzi AI still has a long way to go before we can finally tackle the problems in CJK type design. Co-creation with Hanzi AIs is already happening in the industry. I surely believe we will one day learn how to make the best working with AIs in creative industry. And finally, let tech liberate our creativity. That's all for this talk. Thank you for your listening.
Okay, thank you for interesting session.
Yeah, thank you.
And in the chat room, there are a lot of questions. I think you already answered some of them.
Yeah, I'm trying to answer the questions.
Yeah. Siva was asking, has the AI-based Gaiji generation been published? You said not yet?
Not yet, yes. Um, in order to get the best quality, you need to train the model, so it's still an offline method for most of the cases. If you want a new style, it's necessary to train another model for that.
So you need the original data for
Yeah,
yeah.
yeah, it's a matter of data and training with the data. Yeah,
Mm.
it's offline.
Mm. And Siva is also asking, is there a GitHub repo? And I don't know which kind of a repo he is asking, but I think you have already answered him with about your open source growth sense, I think.
Yeah, yes, GlowSense is already an open source project. And I guess he is asking about um, the method for generating gaiji. That method is super big. We haven't decided to put it on GitHub. Yeah. Um,
And
yeah, still, the models that are used in this method are already open sourced by others. Yeah. Generally, some image-to-image translation models can already do great on this task.
good. And Philip is asking, what do you consider of the biggest challenge for vector graphics or vector font generation?
Currently, the Hanzi AI field came out of the image synthesis, which is a domain of computer vision, and computer vision are based on images. Images are matrices, and matrix is very different to vector graphics, which is some kind of series data. It's like a time series. It's something like language or something. It's not an image. Yeah, so it's totally different. We can't use the common computer vision methods to apply those on the vector graphics. And yeah, we still have a few knowledge about that.
Yeah. Actually, I have see some of the project, not yours, but the other projects also in happening in Japan. They have the AI learned, but what they get is a rasterized bitmap image. So
Yeah,
when you need to go back to maybe go back to the graphics for the vector data, it is not good. Mm.
yeah,
Especially filtered trace, you have so many not good points from the designer's view. Mm.
yes. As far as I know, currently they do such things by auto tracing algorithms.
Mm-hmm, mm-hmm.
Um, yeah, so you can't get quality vector graphics that is crafted by the designer's hands.
Mm-hmm. Yeah, yeah, it's not easy. Mm.
Yeah, definitely not easy.
Siva is also saying that actually, has anyone tried using an RNN recursive neural network to generate vector outlines? Is
Yes, such networks. I know there are a lot of people trying to do that. Actually, there are a lot of papers using RNN or some other models that can process the series data and apply those methods on the vector graphics, but they are not doing very well on the Chinese characters. Some of them apply those methods to like Latin letters or icons, but on Chinese characters because they are too complicated. it doesn't get very good results. So there's a long way to go before we can finally see a deep learning model to learn the vector graphics, I think.
So the problem for the Chinese is still it's too complicated.
Yeah, it's too complicated. The structure is much more complicated than the Latin counters.
Yeah. Okay. So sorry that we cannot get John Ray here in the speaking in the room now. He has connection problems and he cannot join with us. But yeah.
Yeah, and I saw Philip is asking different numbers of control points. Yes, that's an headache.
Yeah.
Different numbers of control point, that's an headache. It's not a vector, it's a series data. That's the problem. If it would be a vector, things would be much easier.
Yeah.
Oh, thank you, Philip. That's a very good question.
Okay, I think yeah, there is still a very long way to go, but yeah, we can get the good approach.
Yes, we want to make it practical, like joining up the AI and the traditional parametric methods to do what we can do now.
Never mind. Yeah, we can go step by step and have a trial and error, and there will be some good, interesting things to for use for the future. Yeah.
Yeah.
Okay, I think we can close this session. And thank you so much. Thank you, Yehang and Chen Zewen, and also Zhang Rui, who cannot join with us. And thank you so much, people, who join us. And you are all welcome to go to the hangout room. And I think all of you, all of the speakers, can also join with us, and you can talk much more about all the details, or maybe some other things together. Okay. Thank you for your joining.
Thank you, Eric.